Often the reason you start writing tests because you realize your software is breaking and you want it to not break so much. But this is also sort of the weakest of the goals because it doesn't change the way you build the software minute to minute. At best, it changes the way you release the software. You don't release broken things. The second goal you can have from tests is to prevent fear minute to minute when you're actually building the software. And this sounds similar to preventing regression, preventing bugs, but it's not the same thing because you can prevent bugs with a 4-hour test suite, and many people do. You can gate your release on that. But that doesn't change the way you actually hack on the code. So preventing fear is being able to change things minute to minute or second to second and have the tests verify those changes all the time, constantly as you're working. Obviously, that's where speed comes in. The third goal for tests is to prevent bad design, to learn to write your tests in such a way that the way your test is written makes it difficult to write bad code in the production side. And likewise, it makes it easy to write good production code. I'm not going to get as much into this because this is a very, very subtle topic and it's sort of out of bounds, but I want to mention it because this is sort of the holy grail of testing. So 3 goals: prevent regression, enable refactoring by reducing fear, and improve design. So that's all about test suites. I don't want to go all abstract and theoretical on you, as I tend to do. Instead, let's talk about a specific system test, a specific example, and see what that means. I have a video that I think I actually showed last year at PyCon in my talk. This is of a very, very large system test running. So I'm going to start it. It fires up the application. It's sort of connecting to the server, and then this is a backup system, so it's adding a directory to backup, it does the backup, and then it's done. This is about as big as a test gets in terms of system scope, because that hit everything. That hit the client app, it hit the back-end servers, it hit the data storage, it hit everything. Obviously, dissecting that would take a while, so I have a little bit more synthetic example to dissect in this talk. The name of this test, this is going to be for a Django app, and the name of this test is Test That Spam Posts Are Hidden. I'm going to step through it starting at the bottom, which might be weird if you've never done that, but it turns out that writing a test from the bottom up actually is much easier and usually makes more sense. So if we look at the name of the test, Test That Spam Posts Are Hidden, it's easy to translate that directly into an assertion. I can assert that some spammy text does not come out in the response from the Django view. And then that gives me a hook to start backing out what else I need. I have a free variable response. So what is that? That's the result of invoking a specific view that shows a discussion for some specific discussion object. Of course, I need a post in that discussion to be marked as spam so I can see it not come out. So I'll invoke the mark post as spam view. Forgive my extremely non-restful URLs here. In order to do that, I need to be an administrator, so I will log myself in as Alice, the administrator. She's the protagonist in the story. Bob is the antagonist. I need a discussion to show, so I will new the discussion up and save it. And I need that discussion to be associated with a post that is spammy, so I'll stick a post in its posts collection that is posted by Bob, the spammer, and it has spammy text. And then finally, Alice and Bob are just users, and Alice is an admin and Bob is not. So that is the test. Now, why is this a system test? Why is this not a unit test? Well, let's go through it again, except this time, instead of talking about what it does, let's talk about what it depends on. What are all the things in this test that could cause this test to break? First of all, we are dependent upon the flag in the user, the admin flag. So if that ever changes, then we will fail. And in fact, if the signature of those users changes in any way, we will fail. We are dependent upon the signature of the discussion. If that changes, we will fail. We are dependent upon the relationship between discussions and posts, the fact that it's named posts and the semantics of it. And we are also dependent upon the signature of the post we're creating. If that changes, we will fail. We're dependent upon the fact that that discussion, as created, was valid and savable, both from the perspective of the database and the perspective of any model-side validation. So if that changes, we'll fail. We're dependent on the entire authentication subsystem because we said log in. We are dependent upon the URL of the view we hit. Now, I could have done reverse, but then I would just be dependent on the routing table instead of the URL. We're dependent upon the signature, and by that I mean the incoming params, the post ID. So if post ID changes to post, we fail. If a new parameter becomes required, we fail. And we're dependent on any preconditions of the view. If it requires some other destructive operation to happen first, and we don't do that, we fail. Same exact thing for the second view we invoke, URL, signature, and preconditions, but this time they're different URLs, signatures, and preconditions. And finally, even the assertion has a dependency. It's dependent upon the representation of the data returned. So the assumption here is that we're rendering a page that contains the content of the posts. But what if we want to rebuild our application to be JavaScript heavy so that we just render a skeleton page and then that Ajax is in the data? In that case, the response doesn't contain the word spammy, which means this assertion will always succeed because it's a negative assertion. This is one of the dangers of negative assertions, but it also shows you that we are dependent upon the exact representation of this data. In addition to all of that horrible stuff, we are dependent upon the Django test client, which is a non-trivial piece of software, although it's probably not going to change because that's not really their style. We're dependent upon the entire Django router because we are routing full stack. We're dependent upon the request object because the view integrates with it. The response object because the view integrates with it. Third-party middleware that may happen to be there can break us. Our application middleware that happens to be there can break us, especially if it has dependencies on specific database state that we've not set up. Context managers can break us, and in fact, any code that we delegate to from that view, which is probably a large call stack in a real application, any of that can break the test. The result of all of these dependencies is that you end up with what I lovingly call the binary test suite, which is a test suite where it tends to either completely succeed or completely fail. It doesn't give you any fine-grained feedback about what has actually gone wrong. It just tells you you broke something, and you are left to dig through stack traces. In the ideal test suite, you don't have to dig through stack traces because ideally one test would fail and it would tell you exactly what was broken. Of course, you never achieve that. But this is very, very far away from that ideal. This also leads to people saying things like, every time we change the code, we have to update all the tests, which hopefully is being said by someone who realizes they have a testing problem. Often, sadly, is being said by that guy who thinks testing is stupid, and so he argues against it based on his team's failure to test effectively. Finally, what do we get for all of this test fragility we've introduced by creating system tests? We primarily get regression protection and only very specific kinds of regression protection. We get protection mostly against the layers integrating incorrectly. We do not get protection against the different objects, the small fine-grained objects, being fundamentally incorrect, because it is very, very difficult to test sort of fine-grained edge cases and things like that from the outside. It's very difficult to set the world up in this complicated way where this sort of very rare case is triggered. And of course, we don't get any help with refactoring because this is going to be a very slow test suite. You can't run it second to second or probably minute to minute. And we're not going to get any feedback on design because we're not even interacting with a lot of the small objects. So that is a system test. Has value, but also has some problems. Now let's briefly talk about how to fail, mostly with big tests. I have, once again, 3 ways to fail. The first of which is to use Selenium or anything like it as your primary testing mechanism. You will fail. Every single time. What you will end up doing is having a CI server that often looks like this, because either the tests can't be run locally, and if you have that problem, leave this room and go fix it. You should be able to run your tests locally. Or you'll have the problem of a test suite that is so slow that you can't run it before commit. You can't run your 4-hour test suite before committing because you'd have to sit there for 4 hours. So the problem you run into with Selenium is that your tests are so slow that you can't really run them. They give you no kind of fine-grained feedback, and everything's broken all the time, and it is only on release gating that things become fixed. The second way to fail at testing is to write things that you call unit tests that are far too big, that look much more like the system test I showed you. The problem here is sort of subtle and weird, and it is that the runtime of your test suite grows super linearly. Why does that happen? In week 2 of your project, you have a 100 millisecond test suite. You write a new test. It takes 1 millisecond to run. Awesome. Test suite's fast, tests are fast, everything is great, fast feedback. 2 years into your project, that test that took 1 millisecond at week 2, unchanged, now takes 100 milliseconds. The reason is that its call graph has grown because it's interacting with a high-level piece of the system, and the graph has grown and grown and grown. More and more code has been executed. The test gets slower and slower. So every time you change the system, you're adding code and test, which means you're adding a new test, which executes in some time. And the small piece of code you add slows down many existing tests. And this is why your test time grows super linearly and turns into a 4-hour test suite, and then you start paying people to parallelize your tests on their grid, and it's a bad scene. Also, I would like to note that a 100 millisecond test is 240 million CPU instructions, and I don't think any definition of the word unit takes 250 million CPU instructions. So that's the second reason, the second way to fail at testing. The third way is actually about small tests, because small tests are not cure-all either. Writing fine-grained tests around legacy code. What you're saying here is that we acknowledge that this code sucks. So we are going to go in and write tight tests around it that solidify its interface and just bake the badness in forever. This is the worst way to do unit testing, to go into your legacy system and write fine-grained unit tests around bad code. So that's how to fail. Now, finally, I think with this context, we can talk about unit tests. What are they? Why do we care? I have, of course, another video of unit tests running because I am obsessed with test speed. This is from the same system as the first one. I think I also showed this one last year. I pressed enter, it imports for a second or two, and then a bunch of dots come out, and it's done. So that just verified the basic correctness of almost the whole system. There's a bit of legacy in there, but most of the system was verified by that. Here's another one from my friend Corey Haynes. He hits enter, and about 1 second later, he has, I think, 386 dots, something like that, comes out. That's in Ruby, but same performance characteristics as Python, basically, except garbage collection sucks. Now, if you, let's talk about why the unit test is so fast compared to the system test. Let's talk about the dependencies of it, because that's a large part of it. So, excuse me, we haven't talked about the unit test yet. Let's talk about the unit test. Same test that spam posts are hidden. Starting at the bottom. This time, instead of asserting that something came out, let's write it just at the model layer. So we assert that the visible post for some discussion is empty, assuming that there's a spam post in there. We need a discussion, so we create a discussion. It has one post. We need that post, so we create the post and mark it as spam. This is a complete test that tests this behavior at the model layer. This is not a complete test that replaces the system test. You would also need one at the view layer and the template layer if you're into that. So it would take 3 to replace that system test, but they will all be much faster, and you can glance at this and you know exactly what it's saying. Whereas the system test, you have to read through it. It's a story. There's state there. Much more difficult to think about. Now, why is this a unit test? What is the definition by which I can say this is a unit test and the other one isn't? I can't just say, well, it doesn't integrate with as much stuff, because that's a relative measurement. First of all, this tests one object behavior only. If we look at it again, the first line sets up an object, creates an object. It's purely constructive, not destructive. The second line constructs an object. The third line takes an action and asserts that something happened. One action is taken. In the system test, multiple actions were taken. We logged in, that's an action. We invoked the Marcus spam view, that's an action. And then we invoked the discussion view, and that's an action. The second reason this is a unit test is that as much as possible, other classes can't break it. And this is really, I think, the most important part of unit testing. So if we go through that code again, looking at the dependencies, the first line depends on the signature of the post model. It depends on the marked as spam flag being there, and it depends on it not requiring anything else. The second line depends on the signature of the discussion model and the relationship between the posts and the discussion. The third line depends on the existence of the property. But most of these are actually intrinsic to this test. The property existing is what we're testing, so that's not an incidental potential source of failure. That is exactly what we want. The marked as spam flag is exactly what we want. The relationship between the discussion and the posts is exactly what we want because we're testing the discussion's ability to filter. Now, the fact that we will fail if other arguments are required is incidental, and that's unfortunate, but it can be fixed with test object factories, which is another talk. Notice that we are not integrating with any of this large, onerous stuff in this test because we're working right at the model layer. The result of this is that your test failures will look much more like this, much more isolated. It will tell you at least which object's broken, if not which method is broken, which is what you want in your test suite. You also will get a much faster test suite. It's the difference between 400 milliseconds and 40 seconds. At 40 seconds, you can't do the thing that I call TDD. It just doesn't exist anymore. At 400 milliseconds, of course, you can. Finally, this unit test does give us regression protection, although not in the same way the system test did. This diagram sort of suggests that I'm saying that the unit test gives you everything the system test did, but more, which is not what I'm saying. The system test gave you boundary, it tested the boundaries much more than a unit test can. But the unit test gives you much better testing of the fine-grained behavior of the individual objects, and that is most of the behavior of your system, hopefully. The unit test, of course, also enables refactoring because it's very fast. You can have a very fast feedback loop. Test first if you like that, test after if you like that, but in either case, you can go much faster, and that allows you to avoid fear. Finally, it gives you some design feedback because if that 3-line unit test had been 8 lines, I have conditioned myself to the point where I would have been repulsed by an 8-line test for a model. And I would have asked myself, why do I need to set up so much of the world to test this one small piece of behavior? That causes me to decompose it, which causes better system design. Now, as far as how this fits in with system testing, I think that for a team that is currently writing big tests, whether it's Selenium, whether it's traditional Django tests that hit views a lot, I recommend something like 90% unit, 10% system as a goal that you should look to in the short term. If I started a greenfield project today, I would expect 95.5 in the early days, and I would expect it to approach something more like 99.1 unit to system. Now, I feel compelled to note that I have not mentioned test doubles in this talk, mocks. I am the author of a Python mocking library. I have talked about it in the past, but this is not about mocking. This is only about limiting the scope of your test to very few objects. That is easier at lower levels like models, which is why I chose that example because it's very nice. It is harder at the view level in Django or anything like it without mocking. If you get serious about this, you will end up mocking. It's okay. Don't freak out. But you don't have to do it to start. You can start this stuff with totally standard tests that just new up objects and make assertions. With that said, that is the end of the actual content of the talk. We will have time for questions, but I'm Gary Bernhardt. I run Destroy All Software, where I produce screencasts about OO design and Unix and TDD and writing smaller, faster tests. And I thank you guys very much for allowing me to talk to you. Go ahead, my man.
Was that 90-10, is that in time or lines of code or what?
I'm sorry, that was very vague with me. 90-10 was number of test cases. So if you did that, you would actually end up with a suite that was more biased towards system tests in terms of lines of code, because a system test will necessarily be larger. So yeah, 90-10 test case count.
So you said if you were starting a new project today, you'd aim for the 90-10 or 99.1 or 95.5. Does that apply to every type of project? Is there a type of project for which you think there's a totally different ratio or a totally different approach? Or
Right. So that applies mostly to object-heavy systems like web apps that have a lot of logic and not a lot of boundaries. If I were writing, for example, every open source project I maintain is not of that form, and they all tend to have integration tests mostly or almost, or sometimes exclusively, because it's not the right thing, because there's not a bunch of objects containing logic that are talking to each other. It's more about the boundaries to the system, because it's things like test runners, test double libraries, mocking libraries, stuff like that. So that advice is geared towards the web app mostly.
Great talk. Thank you very much.
Thank you.
So my question is about a pain point in unit testing a web app in something like Django is the database. You're never going to have a test suite that runs 240 tests in 400 milliseconds if you're touching the database. And now maybe this is a failing in Django, but if you're working with Django model objects, they're very tied to the database, specifically things like a relationship between post and description like you showed there. Unless you've extended the way the Django model layer works, you have to save the one object before you can associate it with the other object, and that means hitting the database.
Right.
So what's your advice in terms of writing fast unit tests? My experience has been that trying to mock out the persistence layer is a way to fail, and maybe I'm wrong, and I'd be interested in your thoughts on that.
No, I think you're right in that if you're writing model objects that have a bunch of behavior on them, and then you mock out the persistence, that is not a good idea. Because, it's just clear, right? The boundary is too wide there. You're mocking out a very wide boundary that you don't even control, although, once again, Django is very good about not breaking you. But still, it's not a good idea. What I recommend in that case, and now we have to talk about mocking, is take all of that behavior that's on your model objects and pull it out of there into just service classes that are stateless, that interact with the model objects. So view calls a service, the service contains the intelligence, and the service manipulates the model objects. You can still have methods on your model objects that do things like wrap specific queries in class methods or wrap specific mutations when multiple fields are commonly manipulated together. It's okay to have those on your model object and then have the service use those, but if you pull the behavior of the system out into the service and you control the boundary between the service and the model by those methods you've written on the model, then you can mock those out more easily and safely. So that's my basic answer. Others? I don't think I've ever done a talk that generated so few questions.
Answered them all.
I answered all the questions, apparently. Oh, here comes someone.
Since you missed my talk, I'll ask you a question based on my talk.
Go for it.
So you mentioned writing mocks of the models.
Yes.
So if you're adding behavior to model objects, how would you try and would you do anything to try and verify that the mock that you've written has the same behavior as the real thing?
Oh man, that's like 4 talks right there. Let's see. My first talk on that topic is use system tests. You need system tests because they ensure that these small objects you've tested in isolation actually wire up together. So that's my first answer. My second answer is that I don't know about anything in the Python world, but Ruby programmers are actively working on this problem. There is a project in Ruby called RSpecFire by Xavier Shea, which will actually allow you to stub out or mock out collaborators in your tests, but if that collaborator's class is loaded, then it will actually do interface checks and say, hey, you mocked this thing with 2 arguments, but it really takes 3, fail the test. Or you mocked this method that doesn't exist, fail the test. So those are 2 possible paths to fixing this in a dynamic language. In a static language, of course, this problem mostly goes away, at least at the interface level. But yeah, it's a real problem. You need to solve it either with system tests or with some magical tool that I don't think exists in Python yet. That's true. The comment was that mock by Michael Ford will do interface checks. Although I wasn't thinking of that because that's sort of not backwards, but the opposite approach, where he does it up front, whereas RSpecFire does after the fact verification. The problem with mock is that you have to have the thing loaded to construct that mock, which means if you want to test one small source file that depends on none of Django, for example, you have to load Django because you have to load your model because you have to mock it. Whereas RSpecFire does not work that way. It will run in isolation if you want it to. So, but you're absolutely right that there are tools that do that in Python. I misspoke. Anyone else?
Right here in the back.
Oh, yeah.
So you mentioned, unit testing legacy code fail. Could you just go into detail about how and why in particular?
Sure. The question is, why is it such a bad idea to unit test legacy code? Testing legacy code, of course, is a good idea, right? Because testing code is a good idea. The problem arises when you have the 1,000 line class that is untested, and so you go in there and you start writing very fine-grained tests around the edges of it, which solidify the edges. And actually, out of everyone in the Python world, I may be the worst offender in this case because my mocking library Dingus can actually magically mock the entire outside, everything on the surface area of your class under test, and people use this for legacy code, and it was a terrible mistake. So if you're doing that, stop it. But the answer, the thing you want to do, is to put a big test around your legacy class, a system level test, and then with that very basic confidence that you're sort of not breaking things, you want to start pulling pieces out and maybe unit test those. Or you want to re-TDD replacements for existing methods, which is a whole subtle topic. But if you need to do this, if this is a problem you have, you want to read Working Effectively with Legacy Code by Michael Feathers. This is sort of what Feathers does, is rescue legacy code, and he's been doing it for a long time, often in much more adverse development situations like C++. So working effectively with legacy code is a wonderful resource to understand how to do that much better than I do, because I'm honestly not very good at it at all.
You mentioned integration tests at one point in your talk and system tests the rest of the time. Do you distinguish, or was that the same?
I apologize. I tried not to do that, but I failed. The question is, I mixed up system test, or I mixed the terminology, system and integration. This terminology has a terrible, long, confusing history. And basically, the main distinction I'm making is between a unit test that tests one thing and any kind of integrated test that tests multiple things. The other distinctions are useful, like system versus integration and acceptance versus everything else. Those are all useful distinctions, but there are other talks. But yeah, I'm just distinguishing between fine-grained unit test versus larger integrated test. What about functional tests? Functional test is mostly a synonym for system test as I use the words. The problem here is that this is like asking someone whether they're a liberal. Like, it depends on the observer. It depends on their definition. It depends on your definition. They might not line up. And then you end up having conversations where you both think the other one's wrong, but it's really because you're talking about different things. So I try to avoid these words entirely if I can. Yes. Yes. Augie's saying functional test means very different things in Python and Ruby communities. This is because Rails broke the terminology in the Ruby community. They turned it into meaning controller test, I think. I don't know. The first thing I always do is delete that test directory when Rails generates it. But yeah, you're absolutely right. The terminology is a mess. Yeah.
You mentioned using Selenium as being full of fails for your large scale, or for your subclass of testing. I was hoping that you could go into a little more detail on that. Like, when is Selenium appropriate? When do you avoid it?
Right. So, right. When is Selenium appropriate? I don't think Selenium is evil. I hope I didn't give that impression. The problem I was referring to is if you use Selenium to test everything, if you use Selenium to test fine-grained behavior where you could have just written a unit test on one object, that is where you will run into huge problems. Selenium is useful for writing the large-scale system tests that you absolutely should have at the top of your system. I mostly work in Ruby these days, and I use Cucumber driving Capybara driving a headless WebKit browser in process. So I don't think it's evil. It is really hard to do that well, but I don't think it's inherently evil. It's just something that you should not run away with, and especially don't start paying non-programmers to generate a giant Selenium test suite, because you will quickly be paying people to parallelize it for you, and you'll be spending your whole life maintaining it. Anyone else? Yeah.
So you say, well, you don't. You say, let's say I have a very big test sheet of mostly system tests, which I now want to convert into unit tests.
Right.
How do I make sure that, because I want to remove those system tests eventually, how do I make sure that my new unit tests are covering everything?
The question is, how do I convert a system test suite into unit tests and ensure that they're covering everything that the system test was in the first place? I don't know. Ask Michael Feathers. I think that sometimes it's fairly obvious. Like if you looked at my system test example where I was invoking views and all that stuff, you can think about the assertion that's made at the end and ask yourself, what had to happen for that to be true? You had to set up the model in a certain way. You had to have the view invoke the model and return something to the template, and you had to have the template render it. And those are sort of the 3 unit tests that I would decompose that into, although maybe not the template test, depending. So sometimes you can look at it and it's fairly obvious if you just think about what's happening. When it's not so obvious, that is probably the test to punt on until it's the only one left, and then maybe you have that problem. But that's a good problem to have. I think that most system tests that I look at least, there's some kernel of it, often expressed in the name of the test, that is really what it's trying to do. And you can decompose that usually into 1 or 2 very small unit tests at model layers often. But sometimes it's going to be really hard, and I would just leave those because your goal is not to eliminate system tests. Your goal is to speed up your test suite, get faster feedback, get more fine-grained failures, and you can get most of the way there leaving some of that cruft behind. I know it's not much of an answer, but right. Code coverage can help, but the problem is that then you have 2 problems because now you're going to end up with people gaming that metric, and you're going to get obsessed with the number and stuff like that. Branch coverage helps. Coverage.py supports branch coverage as of, I think, 2 years ago now. That's a little bit better, but then full branch coverage becomes a very difficult thing to achieve, and it can actually, you can once again become obsessed with the metric over the results. But with that said, one good way to decompose a system test, maybe, is compare the coverage before and after you decompose it. If the coverage is the same, then you're at least hitting the same lines of code. So, and you are going to have more assertions in the unit test, hopefully. So it is a useful thing. Anyone else? All right, I think that seems like a good point to end it. Thank you, guys.